Hi, today I would love to do something new. So I brought with me my paper tablet. You see the screen shared here. So what I'm going to do is I'm going to read a paper and trying to get the most out of this. This is for me a quite interesting paper. Grad-TTS, a diffusion probabilistic model for text-to-speech. Already quite interesting because, well, it's quite telling what the whole thing is going to be about. Of course, well, I do a lot of artificial intelligence, so this comes from artificial intelligence, machine learning, deep learning. So what you see here already, quite relevant, it's text-to-speech. So that's the use case. So given a text, a string, synthesize some audio from that so that you can actually listen to it, which is quite nice. Another thing is, well, diffusion probabilistic model, also fairly interesting. It's a diffusion model, which means that it's something that removes noise. Maybe I'll talk about it later in a little bit more detail. And well, the last couple of months, we were really excited. So everyone, not only me and myself, everyone else about those diffusion models for image generation, stable diffusion. Fine example. DALL-E 2, also a diffusion model. They are quite powerful when it comes to text image generation. Sorry, not text generation. So let me see. Let me try to get the most out of this. Tiny little detail on the side. August 2021. We now have the end of 2022. So it's a rather young paper. It's not the newest paper, but also not very old. Well, you know how to read a paper. What do you do first? Well, first thing you do is you read the abstract, and then you go to the conclusions or summary, depending on where we are. So let's see. Recently, denoising diffusion probabilistic models and generative score matching have shown high potential in modeling complex data distributions, while stochastic calculus has provided a unified point of view on those techniques, allowing for flexible inference schemes. Already quite interesting. Denoising diffusion probabilistic models. Denoising diffusion. Denoising diffusion. So the idea is that you take a sample, and the sample could be an image. As the prime example that you have a sample, which is an image. And what you can do is you define a process how to add in a stepwise fashion noise to it. So randomness to it, which is fairly easy. You don't need a new network for that. It's just something that you implement. The other direction is way more interesting. Given a picture where you have some noise in it, how to remove noise in a stepwise fashion. What this allows you to do is, well, given noise only, it could also distill or get a picture out of the noise by gradually removing the noise. So what you would see is noise at the beginning, and slowly you see the image coming from that. And here I would believe, well, this is about text-to-speech. So it's a fancy name, Grad-TTS. A novel text-to-speech model is also very interesting. A score-based decoder, quite curious what a score-based decoder is going to be. And, well, here, producing MEL spectrograms. Producing MEL spectrograms is something very, very relevant here. It turned out that when you do audio processing with deep learning, it's always good to use a MEL spectrogram as a first feature. So you use an algorithm. You don't need a new network for that. That takes a piece of audio, which can be anything, music, sound, and text, and does a several step Fourier transformation. Yeah, that's right, Fourier transformation. And what you get is something like an image, and the image would have two dimensions. The first dimension would be a time dimension, and the second dimension would be a frequency dimension. So it takes sound, which lives in the time domain only, which is a waveform of some sort, and it maps the waveform to a 2D image. And well, with 2D image, you can do image processing. So that's one direction where you use it as a feature. In generative deep learning, it turned out that, well, using MEL spectrograms is also a way to go. So the idea would be that you not generate the sound, the waveform directly, but you would generate a mouse spectrogram first, representing the sound, and then you would somehow, and I'm quite curious how we do it here, you would then somehow map the mouse spectrogram back to the sound, which is called mouse spectrogram inversion. There are quite a lot of approaches how to do that. Because the trouble is the mouse spectrogram is not really lossless. It's the opposite. You lose a lot of information, including the wave, the phase of the waveforms, which makes it a little bit tricky to reconstruct, but well, there are approaches to do that. By gradually transforming noise predicted by encoder and aligned with our text input. Okay, gradually transforming noise predicted by encoder and aligned with text input. Aligned with text input. So you have two things. It's not only a model that starts with noise, removes noise from it, and generates mouse spectrograms from that noise. It is also aligned with text input. Well, I think it's two things. The first thing would be, well, it's text input, which is the utterances that you want to hear, the words, but also alignment in space, like how long a word would be. At least this is what I would expect. The framework of stochastic differential equations helps us to generalize conventional diffusion probabilistic models to the case of reconstructing data from noise. There it is again, reconstructing data from noise with different parameters, and allows to make this reconstruction flexible by explicitly controlling trade-off between sound quality and inference speed. Okay, that's fairly interesting. Controlling trade-off between sound quality and inference speed. Well, I would expect that if you want quicker inference speed, which might make sense when you use this in a conversational agent, you don't want to wait 10 minutes until you can hear the text to be spoken, but maybe a couple of seconds at most. And turns out that if you would like to have, at least I would expect, like high speed in inference, sound quality would go down and the other way around. So you have to find your own sweet spot for that. Subjective human evaluation, there you go. Always. You can do so much deep learning, but for many generative tasks, especially, you still have to go through a subjective evaluation. You have to show generated samples to people and ask people what they think about that. And it shows that Grad-TTS is competitive with state-of-the-art text-to-speech approaches. Mean opinion score. So this is really subjective. Unfortunately, having something objective, well, don't have it here yet, but let's see. Okay, that's fine. So that's the abstract. Let me see. I'm curious about how well the results are. So lots of things to read. 13 pages. That's quite something. So we have experiments, subjective evaluation here, objective, end-to-end conclusion. Okay, they have presented Grad-TTS as promised. The first acoustic feature generator utilizing the concept of diffusion probabilistic models. So we have to realize that this seems to be the first approach for audio or for acoustic feature generation. Might be even for audio in general, using diffusion models. The main generative engine of Grad-TTS is the diffusion-based decoder that transforms Gaussian noise, quite a lot of randomness, parametrized with an encoder output into mouse spectrogram, while alignment is performed with monotonic alignment search. So, okay. That's all quite relevant. The model we propose allows to vary the number of decoder steps at inference. This is quite good. And synthesized to control the trade-off between inference speed and synthesized speech quality. Despite its iterative decoding, Grad-TTS is capable of real-time synthesis. This is very good. This is very, very good. So at least what I read here is, remember the denoising steps, where you take random noise, you have it somehow informed with some text, and then you remove the noise in a stepwise fashion until you get a mouse spectrogram. Seems to me that you can go down in the number of steps so that you can have faster inference. So the generated voice might not sound so nicely, but well, seems to be okay to do this trade-off. And well, as you know, once the machines are way faster, then well, there you go. We don't care about that anymore. Despite its iterative decoding, Grad-TTS is capable of real-time synthesis. So you get it in real time, which is quite good. Iterative decoding, yeah, that's the thing. Unfortunately, with diffusion models, you don't predict once. You predict a couple of times, maybe 50 times, maybe 100, maybe 1,000 times, like this, removing noise from the noise. Moreover, it can generate MEL spectrograms twice faster than Tachytron 2, while keeping synthesis quality competitive with common TTS baselines. Okay, so there you go. Beating someone else's work, which is quite fine in academia and research. So let's see, a couple of references here. Just quickly check. I don't think you have anything. Sometimes those papers have a treasure trove at the end. Ah, there you go, appendix. Solving forward diffusion. Let's see if there's something interesting, because turns out that with the things we usually talk about, so everything has to do with deep learning, they usually run out of space in the papers, and sometimes they put very, very interesting things right in the appendix. Like, for example, model architectures. And see appendix A of the model architecture, and then say something about training, how much data they used, what kind of data sets, evaluation of the data sets, statistics about the data sets, and training time, and how much training time is spent in, well, matter of GPU hours. Okay, so fine. So far we know this is all about generating MEL spectrograms from text. Still, I don't know how to go from those MEL spectrograms to audio, but maybe it's hidden here. Okay, then we have something else. So usually when you do research, after reading the abstract, maybe also the introduction and the conclusion, it's your decision to make if you would like to continue this journey, learn more from the paper, or if, well, maybe the paper is not what you were looking for, so then you would skip it. So don't hesitate to say no to papers. It's quite fine to save some time here. Well, I'm curious. I would like to learn more. So let's quickly go through the whole paper. That's what I usually do. I do the skimming. Well, let's not do really some skimming, but let's see what we can find here. Okay, introduction. Same thing. Usually is repeating the abstract in the same abstract and then adding something to this. So it's modern text-to-speech. There we go again. Often consists of two parts. Designed as deep neural networks. The first part converts the input text into time, frequency, domain, acoustic features, feature generator. And the second one synthesizes raw waveform conditioned on these features, a so-called vocoder. So this is important. So what they're saying here, that it's almost commodity. If you would like to generate audio speech, that you would train two neural networks. One neural network would create audio features like MEL spectrograms, and the second would go from MEL spectrograms to waveforms. And in text-to-speech, this is called a vocoder. It also goes by the name, and I remember that I said it before, it's a MEL spectrogram inversion or inverter, or the more general case, because vocoder comes from voice. So maybe it doesn't make sense if you train it on music. Introduction as conventional state-of-the-art autoregressive models. That is quite interesting, autoregressive models. Diffusion models are not autoregressive. Autoregressive is you start with something and you add new features to it and generate more pieces of a sample, like generating or predicting the next word in a sequence of words, and in MEL spectrogram, the next slice of a MEL spectrogram. Diffusion models, on the other hand side, they are not autoregressive. They are not adding more. So you have at the beginning to specify how long or what shape the sample is going to have, and then generates with the inverted diffusion. Okay. Used for and WaveNet. Okay, used for, so there's an example using Tachytron 2 for MEL generation, and another example from MEL to audio, WaveNet, I think it's from Google, used as a vocoder, and this is the beginning of a neural TTS era. Later, other popular generative modeling frameworks such as generative adversarial networks by Goodfoley, GANs, very important, and normalizing flows, never used that, were used in the design of TTS engines for parallel generation with comparable quality and synthesized speech. So you see, this is not something new. People have been working in this. What is new is the diffusion model here. Let's continue. Since the publication of the WaveNet paper, 2016, boy, it's not so long ago, and so much has changed. There have been various attempts to propose a parallel non-autoregressive vocoder which could synthesize high-quality speech. So, well, it could take quite some time if you have in a sample to predict the next piece of the audio wave, and after the other, after the other, after the other. To propose a parallel non-autoregressive vocoder, so this is MEL to audio, which could synthesize high-quality speech. Popular architectures based on normalizing flows like parallel WaveNet and WaveGlow, this is the one that I used, managed to accelerate inference while keeping synthesis quality at a very high level, but demonstrated fast synthesis on GPUs only. Okay, that's sad because, well, you need some GPU compute in order to do the synthesis. Eventually, parallel GAN-based vocoders such as parallel waveGAN, interesting, parallel waveGAN, and hi-fi GAN greatly improved the performance of waveform generation on CPU devices. Furthermore, the latter model is reported to produce speech samples of state-of-the-art quality, outperforming WaveNet. So now, second part, when it comes to MEL to audio, there are GANs who seem to be state-of-the-art, and hi-fi GAN 2020 looks like a very, very promising and, well, it is state-of-the-art, right, isn't it? Among feature generators, so this is the other part. Tacotron 2, 2018, Transformer TTS, 2019, enable highly natural speech synthesis, producing acoustic features frame by frame, autoregressive. They achieve almost perfect mass spectrogram reconstruction from input text. Let's keep that in mind, frame by frame and input text. Nonetheless, they often suffer from computational inefficiency and pronunciation issues coming from attention failures. Addressing these problems, such models as fast speech and parallel tacotron, 2019, 2020 respectively, substantially improved performance, inference speed, and pronunciation robustness by utilizing non-autoregressive architectures and building harmonic alignments and so on and so forth. However, in order to learn character duration, they still require pre-computed alignment from a teacher model. Finally, the recently proposed non-attentive tacotron framework managed to learn durations implicitly by employing the variational autoencoder concept. Oh, quite interesting. Seems to be a development. Autoregressiveness, there's some problems, and one problem is the length of the utterances, or the syllables and the words. So I think maybe this is something that this paper is going to overcome also. Grad-TTS, let's check. Grad-TTS, Grad-TTS feature generator based on normalizing flows. I seem to remember those are the neural networks that you can go back and forth with shared weights, but I might be wrong on that. Can be considered as one of the most successful attempts to overcome pronunciation and computational latency issues typical for autoregressive solutions. Normalizing flows, so 2020, the plot thickens. Grad-TTS model made use of monotonic alignment search algorithm. There's some Viterbi training, finding the most likely hidden alignment between two sequences proposed to map the input text to mass spectrogram. Okay. Alignment learned by Grad-TTS intentionally. Okay, but what's the problem with Grad-TTS? Let's see. Thus, compared with Tacotron 2, Grad-TTS achieves much faster inference, making fewer alignment mistakes. So this is quite interesting. So it's not necessary to really learn all the related work by heart, at least when you read the paper for the first time. Besides, in contrast to other parallel TTS solutions, such as fast speech, Grad-TTS does not require an external aligner to obtain token duration information, as monotonic alignment search MS operates in an unsupervised way. Okay, we're getting there. Lately, another family of generative models called diffusion probabilistic models, DPMs, have started to improve its to prove its capability to model complex data distributions such as images, shapes, graphs, handwriting, and music also. The basic idea behind DPMs is as follows. So you see they're building the story here towards their contribution. So let's see, the basic idea behind DPMs is as follows. We build a forward diffusion process by iteratively destroying original data. We build a forward diffusion process by iteratively destroying original data until we get some simple distribution, usually standard normal Gaussian distribution. And then we try to build a reverse diffusion parameterized with a neural network so that it follows the trajectories of the reverse time forward diffusion. Okay, that's the thing that I said at the beginning. Most important here. Again, here you take a sample. In this case, you could think about pictures, but here mouse spectrograms, something also like pictures. And you would add a noise to it in a stepwise fashion. And what you would train would be a neural network for the reverse of that. So taking a picture with noise or with more noise as an input, and then predicting from it a picture with less noise as the output. And if you do it multiple times, multiple steps, the entire chain, I think it's even a Markov chain, then you get this diffusion model. Stochastic calculus offers a continuous, easy-to-use framework for training DPMs, and, which is perhaps more important, provides a number of flexible inference schemes based on numerical differential equation solvers. Now, this is very, very interesting, that although you would train it on quite a lot of, well, you would train it on a lot of steps, it might not be necessary to use the same amount of steps in inference. As far as text-to-speech applications are concerned, two vocoders representing the DPM family showed impressive results in raw waveform reconstruction. WaveGrad and DiffWave were shown to reproduce the fine-grained structure of human speech and match strong autoregressive baselines such as WaveNet in terms of synthesis quality, while at the same time requiring much fewer sequential operations. However, despite such a success in neural coding, no feature generator based on diffusion probabilistic is known so far. Interesting. So turns out WaveGrad and DiffWave, they go from mass spectrograms to audio with such a diffusion process. Interesting. But the other piece is missing. So those are neural vocoders with diffusion, but generating the features, the mass spectrograms, no diffusion so far. Well, now it's different because, well, the paper is a year old. This paper introduces Grad-TTS, an acoustic feature generator with score-based vocoder using recent diffusion probabilistic modeling insights. Okay, something we already talked about. In Grad-TTS, master-aligned encoder outputs are passed to the decoder that transform Gaussian noise parameterized by these outputs into a mass spectrogram. To cope with the task of reconstructing data from Gaussian noise with varying parameters, we write down a generalized version of conventional forward and reverse diffusions. One of the remarkable features of our model is that it provides explicit control of the trade-off between output mass spectrogram quality and inference speed. Quite interesting. In particular, we find that Grad-TTS is capable of generating mass spectrograms of high quality with only as few as 10 iterations of reverse diffusion, which makes it possible to outperform Tachytron 2 in terms of speed of GPU devices. Additionally, we show that it is possible to train Grad-TTS as an end-to-end TTS pipeline. That is, a vocoder and feature generator are combined in a single model by replacing its output domain from mass spectrogram to raw waveform. Plot thickens. Plot thickens, so it's end-to-end. Now let's see what they do here. No, doesn't work, maybe like this. Okay, let's continue. Now I'm quite curious. That's the introduction, and this is where usually the beef happens. So what I'm interested now is the experiments, not really yet the theoretical, what lies under the, what's the theory behind that, but I'm more curious about like what are the results now and how did they do it? So something very important, you see it here, right? This is the thing that I talked about. There's the diffusion, forward diffusion from data. This is a mouse spectrogram, by the way, to noise. So mass spectrogram here from left to right is time, and this is frequency. So we have low frequencies here, high frequencies there. And you see those glowing things, those parallel lines, those are formants. You usually see it in speech where you have, well, a vowel with overtones. Bright color means high in intensity, so quite loud. And these patterns are usually like telltale signs of what is actually uttered there. So you can see it immediately that this is a voice. Here's the same mass spectrogram, but with little noise, here a little bit more noise, and this almost, you cannot almost see it anymore with quite a lot of noise. So this forward diffusion, again, you can easily implement, just add noise, element-wise addition here on those tensors. This is more interesting. Reverse diffusion from noise here to data and stepwise coming back to that. So, well, I would believe that, well, the only thing that you have to do for training is come up with quite a lot of mass spectrograms and a way how to add more noise to it. It's just an algorithm. You don't need a neural network from that, thus generating samples for your neural network. Okay, perfect. Now we don't need to mark everything. That one. Okay. So we have the forward diffusion, something to read about, those differential equations, and also reverse diffusion. Let's skip this for a moment because, well, I'm interested about, well, how this works. Well, well, how this works, what experiments they did. Let's say here, Grad-TTS. The acoustic feature generator we propose consists of 3 modules: encoder, duration predictor, and decoder. It's a model. Acoustic feature generator, encoder, duration predictor, and decoder. In this section, we will describe the architectures as well as training and inference procedures. There you go. As well, what do you want to do? You want to train models on your data, don't you? The general approach is illustrated in Figure 2. Looking forward, Grad-TTS is very much has very much in common with Glow-TTS, a feature generator based on normalizing flows. The key difference lies in principles the decoder relies on. Okay. Figure 2, inference scheme. Something to consider. So what is going on here? Okay, there you go. There you go. There you go. So we have something here. We would believe this would be the output at the end. So once we run it, this would be the output. This is the final sample that we are going to get. And then, well, there's a mass spectrogram of a longer utterance, and we have to turn it somehow into audio. I guess it's somewhere written here. And here we start. Hello world. It's a text that you would like to turn into this mass spectrogram. We use an encoder and a duration predictor. Has some aligner here, so it looks like tokens. I don't know yet what it is. So it seems to me encoder, duration predictor, these could be deep neural networks of some sort. Here we have the decoder. So this goes in as a condition. We have the process here, and there's the process that actually happens here, and it happens via a UNet. A UNet, it's I'm going to say an encoder decoder architecture as well that you would use, for example, for coloring images, semantic segmentation. So it's usually a neural network where you have an image going in and it gets compressed. No, not really compressed. It gets feature extracted into a latent space, and from the latent space, it gets reconstructed like an autoencoder. But the thing is with UNet, it also has skip connections to re-inject data that you had at the beginning and in between to stabilize the whole thing. So there's a UNet in it. So I'm quite curious, like, what is the encoder? What's the duration predictor? UNet, oh, this is fully convolutional, so I can deal with that one. So long story short, that's what happens doing inference. It takes a text, does something with it, and then in a stepwise fashion, always informed by the some text, generates step by step by removing noise from noise, the mass spectrogram that fits the text. So it seems to me, at least, well-informed guess, that this is how your data set should look like. For training, you need those mass spectrograms, and you also need the texts. Okay. Something more, inference. Training. One of Grad-TTS's training objectives is to minimize the distance between aligned encoder output and target MER spectrum, because the inference scheme that has just been described suggests to start decoding from random noise. Okay, intuitively, it is clear that decoding is easier if we start from noise, which is already close to the target in some sense. Interesting. So it's not really random noise, but it's always already some noise generated with some info. Okay, encoder optimized, respect to both encoder and alignment, since it's hard to join optimization. Now I'm going to the skimming mode because I would like to get the main beef of the whole thing. There's some loss involved. Okay, fine. And where we are, model architecture. Very interesting. Because when you work with these things in practice, you don't think that much about all these formulae. You think more about layers of a neural network that is stacked on top of each other. As for the encoder and duration predictor, we use exactly the same architecture as Grad-TTS. Everyone knows it, right? Which in its turn borrows the structure of those modules from a transformer TTS and fast speech. The duration predictor consists of two convolutional layers, followed by a projection layer that predicts the logarithm of duration. The encoder is composed of prenet, 6 transformer blocks. Aha, there you go. It's transformer with multi-head self-attention and the final projection layer. The prenet consists of 3 layers of convolutions. Okay, fine, followed by a fully connected layer. Okay, so coming back, the encoder, transformer, I would think, well, maybe something like BERT. Maybe you don't even need to have this pre-trained. Or was it? I think in stable diffusion for image generation, this thing is pre-trained, BERT or CLIP. Here, maybe you don't have to pre-train it, because usually those text-to-speech things are rather tame. Well, let me not talk about Whisper yet. The decoder network has the same unit architecture used by Ho et al. To generate 32 times 32 images, except that we use twice fewer channels and 3 feature map resolutions instead of 4 to reduce model size. In our experiments, we use 80-dimensional MER spectrograms so that it operates on the resolutions 80 times f. We then zero-pad MER spectrograms the number of frames f if f is not a multiple of 4. I have to keep that in mind. Aligned encoder output is concatenated. So first and foremost, it's a unit. The units they are referring to were trained on 32 images with MER spectrograms. It's usually a little different, as you can see here. So what they're talking about, 80 MERs, means that the whole thing, this matrix, has 80 rows from base to the high pitch. And this f is usually longer, so they're not square. But well, UNet is a convolutional neural network architecture, doesn't have trouble with non-square images. Quite fine. Still curious how many frames we have? Let us find out. Maybe it's irrelevant, comes from the data itself. Let's see. There you go. Next thing. LJ speech dataset 2017 containing 24 hours of English female voice recordings sampled at 2205 kilohertz. 24 hours. This is quite something to listen to. And 2205 kilohertz. 22 kilohertz is half CD quality. So it might have some trouble. It might have some trouble in the high pitches because, well, no, well, kind of has means that I think we can represent frequencies around 11,000 with that. And we can, well, if you have good ears, you can go up to 20,000 kilohertz, but here you don't have it. Still fine. The most important thing is that the voice that comes in 22 kilohertz is still high quality voice because, well, it doesn't have that high frequencies that would be lost if you don't encode in CD quality, half CD quality. Okay, the test set contains 500 or okay, there's a test set, 10 seconds each, 500. The input text was phonemized before passing to the encoder. Okay, so it takes the text and maps it to phonemes, so a little bit sophisticated syllables. As for the output acoustic features, we use conventional 80-dimensional mass spectrograms. We always saw that, so 80 rows in those matrices. We tried training both on original and normalized mass spectrograms and found that the former performed better. So normalized, which means, well, normalizing, finding the highest numbers in the minimum number, and there you go. Was trained for 1.7 million iterations on a single GPU. But how long? So single GPU, NVIDIA RTX 2080 Ti with 11 GB of memory. Not the newest one. NVIDIA just released the 4 series. I have 2 of a 3 series. 11 GB memory, quite fine. Mini batch size 16. So that's how you make the memory full. And using the Atom Optimizer. Means NVIDIA RTX, if you don't know, very important. It's not an expensive graphics card. It's not one of the Teslas that cost like 15,000 or more, maybe 1,000, 1,500. It's roughly the range. Those are high-end gaming cards, which have quite a lot of power when it comes to deep learning. So this is something that you can actually run at home. So usual setup would be that you have either 1 or 2, sometimes 4 of such similar cards in your computer, and you don't pay 10,000. Or way before, if forecast, you pay a little more than 10,000 euros. But well, 2 cards are quite affordable, and usually those are the under-desk things that you would have in companies for first experiments. So usually I use NVIDIA RTX cards for inference, like trying out someone else's models. But this gives me quite some hope because, well, it's trained on a single GPU. So I don't need a supercomputer to train such a model if I so choose. So it turns out that they could train 24 hours of audio on an NVIDIA RTX 2080. So this is very important, that you at least get some information if you can train it at home, or do you need a supercomputer? Is it something where you have to spend like 1,000 euros, 10,000, maybe 1,000,000 euros? And this is something where I see this is more like the lower end. It's something that you can afford. So diffusion loss at training, well, loss goes down when you train, takes some time. More than 2,000 epochs. But, well, how long? I would doubt that it has been overnight, maybe a week or 2. Usually you don't run those graphic cards 24/7 because they're not really made for that. So they're huffing and puffing and creating quite a lot of heat. Okay, important things about training. So a couple of hyperparameters, loss, and so on and so forth. So there we go, which is already quite something. So far, the story so far, you see me skipping things because this is my first read. I would like to get the main gist out of it. And well, this is the main thing. There's a model architecture with, here you have something like a transformer and some convolutions. And there's a UNet, which is convolutional architecture for denoising. So going from here to here is one inference step with the UNet. It's kind of aligned, and the data set is that you have text and you have those MEL spectrograms. Well, I would believe that the original data set does not have MEL spectrograms yet. They are wave files, which of course you can transform into MEL spectrograms with feature extractor. librosa is a Python package that does it for you. TensorFlow and PyTorch, they also have functionality to do this. It's fairly easy. It's just iterated Fourier transformation. Okay, still very curious. What about, where is it? What about going from the MEL spectrogram to something you can listen to? Because, well, this, coming back, to get this as a generated output of a neural network doesn't help, because you don't want to stare at it and think like, what does it sound like? No. You would like to turn it into a waveform that you can play. Once trained, Grad-TTS enables the trade-off between quality and inference speed due to the ability to vary the number of steps. Okay, so it's faster. As baselines, we take an official implementation of Grad-TTS. So it's for the, I guess, subjective evaluation with the opinion score. Fast speech instead of a tachotron. Recently proposed hi-fi gun is known to provide excellent sound quality. So we use this vocoder with all models we compare. This is the thing. So I think they use a pre-trained Hexagon, which is a mouse spectrogram inverter, using the GAN principles, mapping the mouse spectrograms to waveforms. Well, I actually am quite familiar with that one. I started using it recently, so I'm quite happy with the results. Okay, and then they go through the subjective evaluation, do a study, and so on and so forth, and find out, well, we are better than the others. Objective evaluation, there you go, randomly 50 sentences, and then, well, objective, getting some numbers out of it. After, well, the subjective evaluation, efficiency estimation, we assess the efficiency of the proposed model in terms of real-time factor. Computed on GPU, the number of parameters table 2 contains, so a couple of numbers here, model conversions, encoded parameters, log likelihood, how good it is, and so on and so forth. Okay, additional, so comparison to how fast it is. Quite good, quite good. And end-to-end TTS. This is, I think, a branch here. The result of our preliminary experiments show that it is also possible to train an end-to-end TTS model as a DPM. In brief, we moved from UNet to WaveGrad. In Grad-TTS decoder, the overall architecture resembles WaveGrad conditioned on the aligned encoder input instead of ground truth. Although synthesized speech quality is fair enough, it cannot compete with the results reported above. Aha, this is very important. Although the synthesized speech quality is fair enough, it cannot compare with the results reported above. We do not include it in listening tests, but they have some samples here. So it turns out they also branched out, did another experiment where, at least from my understanding, let's see, experiments there, where they do not work on the mouse spectrogram, but they use some other neural network to work on the waveform directly. Seems to work. Architecture less complicated, but well, at least what they found out, the results don't compete. So it might make sense, at least for a while, to use diffusion on the mouse spectrograms. End-to-end TTS. Well, there we are. Future work. Quite interesting to have a look at this as well. And well, what I would usually do in order to find the next papers to read, I would go to connected papers and see, well, who cited this and which are the papers who cited this paper that were also cited a lot because, well, somehow indicates some quality. End-to-end speeches. Okay. So it looks quite nice regarding DPNs. So, long story short, in a couple of minutes, we went through this paper, found out it's text-to-speech using diffusion models. So what is going to be trained is something that goes from a text via transformer and CNNs using UNet that undiffuses that, well, diffuses, that denoises some noise distribution until we get the mouse spectrogram. So in inference, the first thing you would do is you would put in the text and it would generate in stepwise fashion this mouse spectrogram, and then you just throw it into Hexagon and get a synthesized speech. It's quite interesting. And well, to tell you the truth, especially with the UNet in the middle, this is very close to some of the more traditional image generating diffusion models where you would also use the UNet on images in order to remove noise and from noise to generate those images. And well, what I find most appealing is that while you trained on 24 hours of text or 24 hours of speech, which is a lot to listen to, trust me, it still works on fairly commodity hardware. You would not train it on your Mac, and no, not on your Lenovo ThinkPad, but well, this is a graphics card that you can easily get. Okay, so usually now would be the time for another decision. Like if you're curious about the underlying mathematics and theory behind that, well, there's a whole chapter about that. Might be interesting to dip deeper, but I usually advise to skip this at least for a moment and try to take this paper and get it up and running. Fortunately, getting up and running doesn't mean anymore that you implement it. It's a nice, don't get me wrong, it's a nice exercise to implement it, but well, usually they have a GitHub repository somewhere. So what you would do is you would well, Command F, and hopefully you find somewhere a GitHub repository. Let me just quickly check if there's a GitHub repository. So Grad-TTS GitHub.io, this is the page where you have the demos. Maybe the source code is mentioned here somewhere. There you go. No, this is fast speech. Well, don't have the Control F here. No, it doesn't have it. Or maybe, no. Usually it's somewhere on the first or second page where you get a footnote. There's code. Ah, there you go. Even earlier, the code is available. We know a speech backbone stream and Grad-TTS. So this is available, hopefully also with training. So a good exercise would be take a data set, maybe the data set mentioned here, or a new data set, and then train it. Train the model on the data set. So, well, this is how I usually go through papers that I find most interesting. Was rather quick, but well, when you do your PhD, you learn these things. So, well, hope you enjoyed this journey. Thank you very much.